Okay, well, thank you everybody for being here. Today we are honored to have Nan Chen participating in our community meeting. I will say a few things about Nan. Nan Chen is an assistant professor at the Department of Mathematics, University of Wisconsin-Madison. He is also a faculty affiliate at the Institute for Foundations of Data Science. Dr. Chen received his PhD from the Curran Institute of Mathematical Sciences and the Center of Atmosphere and Ocean Science in New York back in 2016. He worked as a postdoc research associate at NYU for 2 years before joining UW-Madison. Dr. Chen's research interests lie in applied mathematics, geophysics, complex dynamical systems, stochastic methods, numerical algorithms, and general data science. He is also active in developing dynamical and stochastic models and using these models to analyze and predict real-world phenomena related to atmosphere, ocean science, climate, and other complex systems with the help of real observational data. He is also a member of the US CLIPR Working Group on ENSO conceptual models. He has received several awards, including the Kurt Friedrich Prize for Outstanding Dissertation in Mathematics and the Young Investigator Award from the Office of Naval Research. Today, he will be talking about Lagrangian data assimilation and uncertainty quantification. Welcome, Nan. Thank you, and please go ahead.
Yeah, thank you. First, I want to say thank you to Pierre and Jonado and the other organizers to give me this chance to present my work. And I look forward to hearing feedback from the audience. So today I will discuss Lagrange data assimilation and uncertainty quantification. So my talk will contain 3 parts. First, I will spend a little bit of time giving a background about data assimilation, especially Lagrange data assimilation. And then the next 2 parts will be related to my own research. First, I will discuss these mathematical theorems and the schemes of an efficient Lagrange data assimilation. So I will talk about this framework and the application to this Lagrange-Euler multi-scale data assimilation, or lambda. Then I will make use of this Lagrange data assimilation to discuss a few related UQ questions. First, it's about how to quantify the uncertainty in the Lagrange data assimilation solution. And the second is about this eddy identification, which is something ocean scientists care a lot about. And if we have time, I will also briefly mention about how to optimally deploying Lagrange traces in the presence of uncertainty. So first, a background. So data assimilation is actually a very well-known method. And the idea of data assimilation is to combine a numerical model with observations in a certain optimal way. And the goal is to improve the final results. So why we have to combine these 2 things? Because first, the model is never perfect. The model is usually very chaotic and has uncertainties. So uncertainties may come from the imperfectness due to our lack of knowledge, or it may come from the finite resolution in the computational power, or it may come from noise and other things. And on the other hand, observations are also not perfect because observations will contain noise. And in many cases, our observations are only available for a subset of state variables. So for example, if we want to solve a coupled atmosphere and ocean system, maybe our observations are only available for atmosphere, but not for the ocean. So that's why this data assimilation will be very important, because it can combine the useful information of both parts, then we try to get better results. So data assimilation was initially developed in this field of numerical weather forecasts, and it was used to improve the initial conditions for a numerical forecast model. And the reason to do that is these numerical weather forecast models are very chaotic. A small initial error can kill your forecast scale. So we want as accurate results as possible as our initial condition. But nowadays, data assimilation has become an essential tool for many applications. For example, the optimal state assimilation, inferring the unobserved state variables, dynamical interpolation of missing data, parameter estimation, and it can also be used to help control machine learning and many other applications. So the basic mathematical principle of this data assimilation is actually very simple. So let's say U is our state variable we want to estimate, and V is our noise observations. So usually V is a function of U plus some noise. Then the underlying principle of data assimilation is just this equation. So we aim at solving this so-called post-tail distribution, which is a distribution of the state we want to estimate. So it's a distribution of U, but it's a state given the knowledge from the observation. So that's why it's a conditional distribution, PU given this observation V. It's different from PU because PU is usually computed from the model. You run the model forward without using any observation. You get this forecast distribution. And this one usually contains more uncertainty than your posterior. And the reason we can reduce the uncertainty is we have this likelihood function, which tells us about the information from observations. And you can think in the way of this figure. So you have a model forecast, which gives you this like red area. So it's not a single point because the model contains uncertainty. And meanwhile, even though you have a single value of your observation, you know your observation contains uncertainty. So you would rather put some confidence interval around it. So either of them is perfect. But if you can smartly combine them in a suitable way, then you may reduce uncertainty and you may get a better state estimation. So depending on when the state estimation and the observations they are incorporated, data assimilation can usually be classified as either filtering or smoothing. So both of them will satisfy the previous Bayesian formula, but the only difference is that filtering will use the information only in the past to improve the initialization of the real-time forecast. Because you want to do forecast, you cannot use future information, right? But smoothing is a method which you can use observations in both the past and future. And usually smoothing is used to do some post-processing of the data, for example, to remove the noise, to recover the unobserved variables. So sequential data assimilation is something people use quite often in practice. And the idea is the following. So you try to divide this entire procedure to two parts. So you start from some initial value, you run your model for your forecast, you get a distribution. Then you have your observation, you combine your observation with this uncertainty and the forecast distribution to get a posterior. So if your model is linear and if the noise is Gaussian, then everything becomes linear and Gaussian. And this is called the Kalman filter, which is a very famous method. And the good thing about Kalman filter is that closed analytical formula will be available for solving this posterior distribution. So everything can be written down clearly. However, in practice, we know most of dynamics are nonlinear and they have some non-Gaussian features. And particularly, they have this high dimensionality issue. So usually in practice, we have to do some approximations. So people use ensemble methods or particle methods to do a lot of these tricks to approximate the solutions. These methods are called ensemble Kalman filter and particle filters. And similarly, you can develop ensemble particle methods for smoothing. So Lagrange data assimilation is related to these Lagrange tracers. And Lagrange tracers are these structures or floats which follow a path of fluid movement. So I don't know if you know this famous story. So in 1992, there was a ship which contained many of these yellow ducks. And it had an accident in the center of the Pacific. Then these yellow ducks were released because of that accident. So after several years, people found these yellow ducks were everywhere. Then people started to think about what happened. Then realized, because these yellow ducks can be traveled or transported by the ocean current. So that's why they are everywhere. Then realized, if we can catch the trajectories of these yellow ducks, that can be a very useful observational information, helping us recovering the ocean current. And so, of course, nowadays, we are not using these yellow ducks. We use a lot of different devices to we treat them as Lagrange tracers. So this figure is a like famous one from UCSD, this Argo program. And these devices, they will just stay in the ocean and they send signals back to a satellite so we can trace the trajectories like these dots. And if you think about Lagrange tracers in the atmosphere, you can also use these balloons. And in the Arctic area, these sea ice, these pieces can also be thought about as a surrogate about the tracers. And even some garbages, if you can trace them, they can be nice tracers. So these Lagrange trajectories have been directly used to study these underlying flows, and they were used to infer the Lagrange coherent structures and quantifying the dispersion. But we can also combine these Lagrange trajectories with models, no matter dynamical models, statistical models, and we can put them into the data assimilation framework, right? Just observations become these trajectories. So Lagrange data assimilation is such a method where you treat these Lagrange trajectories as your observations. So once you have a model, you run that for a forecast, then you incorporate your trajectories into your forecast, you will get a posterior distribution that helps you get a better state estimation. However, I do want to point out one fundamental challenge in the Lagrange data assimilation. That is, the observation process in the Lagrange data assimilation is always highly nonlinear. So how to understand this claim? So we can see that by using a simple example, say let's consider the spectrum representation of the underlying flow field. Just say you decompose your flow field into the Fourier basis. You consider a periodic boundary condition. So the observational equations will be related to the observations, and the observations are the tracer trajectory, which will be this displacement. We call that x. And according to Newton's law, we know dx over dt should equal to the velocity, right? Equal to u. But now if you want to write down this u, you must realize this u is a function of the location, because at different locations, your velocity is different. So now we decompose this into the Fourier representation. We will have this Fourier coefficient. We'll have this exponential ikx as the Fourier basis. We may also have this eigenvector if this x is x and y is two-dimensional. So assuming the velocity in the two directions, they are correlated. So you have this component, it's a constant. But what I want to point out is when you write down this into the Fourier expansion, you see this x, which is the same as this x, will appear in the exponential function here, which means the right-hand side is no longer a linear function, right? And the nonlinearity is always something that is hard to handle in practice. So if you want to use ensemble Kalman filter or even particle filters, a good method is to do this augmentation of your state. So the idea is you don't treat this as an observation, but you try to put that as part of your forecast model. So your forecast model will contain the equation of your displacement and the equation of your velocity field. Then for your observation process, you have this observation, but you assume you only have the partial observation, meaning that you only have the observation of this x, but not u. So you have a matrix which is 0, 1 here. So this kind of method can be applied to ENCAP, ensemble Kalman filter, and it was used in practice. You can easily incorporate localization and other tricks to help you eliminate some numerical errors. But today I will discuss some additional Lagrange data assimilation methods, and from that we will make use of those tools to discuss some UQ problems. So first I will discuss an analytically solvable Lagrange data assimilation framework with continuous in time observations. Continuous in time observations means we have continuous trajectories. So the motivations of developing this mathematical framework are the following. So first, we want to provide an exact and accurate data assimilation solution because it can avoid a lot of these tuning processes like localization or noise inflation, which has to be done in the ensemble-based method. And if we can write down everything analytically, that can help us write down a lot of nice mathematical formulas to understand the basic properties of Lagrangian data assimilation. And because of this analytical formula, the method will allow us to develop an efficient testbed for understanding the impact of model error and help us to advance the development of many effective approximate methods. So this will help us to build some mathematical guidance of in which situation, what kind of method should be developed. And because of all these analytical formula, the method will allow us to have this rigorous mathematical analysis to understand the performance of the Lagrangian data assimilation. And it will also help us to advance the studies of many related UQ questions. So now I want to present this framework. So again, recall that if we want to do data assimilation, we have to include two facts. One is a forecast model we use to get a prediction. And the second step is we try to incorporate our observation into the forecast result. So basically now we need to develop this forecast model and the observational operator, these two things. So here let's again consider a random flow field represented by the Fourier modes. And we assume we have some truncation, so it's represented by a finite number of Fourier modes. So U, which is a function of x and t, will be written as a summation of different Fourier modes. So U hat k is a Fourier coefficient, exponential ikx is basis function, rk is the eigenvector that connects the two components of this U. So here for the forecast model, let's say we try to use a very simple stochastic process to describe the time evolution of each Fourier mode. Because if we know the time evolution of Fourier modes, we can always reconstruct this entire flow field, right? Because the basis function is deterministic, it's fixed. And the stochastic process we use here is perhaps the simplest possible stochastic process, which is called Ornstein-Uhlenbeck or OU process. It's a linear model. So we have a damping term, which describes the finite memory of your system. And we have this I times this phase term, which means this Fourier coefficient have some oscillations, just like the waves. We have some external forcing. This part is deterministic, but we also have some stochastic forcing here. So of course, you may ask me why we have this kind of equation, especially it's a linear equation. So the idea of doing data assimilation is we actually don't care about each single trajectory as a forecast. What we care about is statistics in the forecast, because when we apply Bayesian, everything is based on the distributions. So statistics here is more important than a single trajectory. So that means even if all these single trajectories are wrong because of the stochastic noise, if we can get a good statistics, this can be a very cheap forecast model and can be applied to high-dimensional case. So there are some motivations of using this kind of simple processes. And actually, if you start with a complicated PDE and you apply a Fourier decomposition, and if your model is nonlinear, then you must have some very complicated nonlinear terms, which will involve maybe a few thousand of these terms, and they can be very complicated, very difficult to compute. But as I said, our goal is to get some statistical forecast. So we can actually effectively represent the effect of these nonlinear terms using the noise to get a similar statistics. So there was some previous studies, telling us this can be done in many situations, especially if all these nonlinearities represent high frequencies, then these high frequency modes will behave like noise. And this kind of idea is also consistent with the previously developed so-called stochastic mode reduction. So these modes can be written as effectively the stochastic processes. Then in terms of observations, we use the previous Newton's law. So dx over dt equals u. So the subscript L means it's L's tracer. So in total, we have capital L tracers, and this little case L just means which tracer we are using here. And we also add some noises here. And this noise can either represent the observational uncertainty, or it can represent some unresolved features which were not characterized by this truncated version of velocity field. But in any case, this will represent some noise or uncertainty from the observation process. So now we have these two sets of equations. So again, for x, we will have in total L equations, and each equation will be two-dimensional because we have x and y, the two directions of the displacement. And for this U hat K, we'll also have many of these modes because this is only one single Fourier mode. We need to write down one such equation for each of the Fourier modes. If we put all these things together, we define a capital U, which contains different Fourier coefficients, and we define a capital X, which defines these different tracers. Then we can rewrite these component-wise equations to this abstract form. And clearly, in the trace equation, there will be some very strong nonlinearity on the right-hand side because of these exponential functions. Basically, Px is a collection of these exponential function, and P is a matrix. So the goal of doing data assimilation, especially filtering, is that we want to recover the flow field given the observations. And again, this will be very different from using the PUT only, because that's only from the model. Now you have the constraint from the observation, so you can expect this distribution will be very different. However, this is a nonlinear data assimilation problem because this term is nonlinear. Nevertheless, the good thing is conditional on the observed tracer trajectories, which means if this x is given, then the process of this U is conditionally linear in both of these equations, right? The second equation itself is linear. The first equation is nonlinear, but if x is given, then U is linear. So this is a very important feature because only with this feature, we can write down this distribution using closed analytical formula, and that will guarantee our Lagrange data assimilation solution can be solved exactly and accurately. So in fact, this equation belongs to this more general framework, which we call that conditional Gaussian nonlinear system. The details can be found in this paper. So basically, if you have two equations, one variable can be highly nonlinear, whatever nonlinearity you want to put, but the other variable should be conditionally linear. And if you satisfy the structure of this equation, then the conditional distribution of y given this x will be a Gaussian distribution because given x, y is linear. Given x, the noise will be white noise. And for a linear Gaussian system, for a linear system with white noise, the distribution is Gaussian. And the analytical formula can be written down in this form. So the details are not important, but as long as you know everything on the right-hand side, you can have all these explicit formula. So you can also build a similar formula for the smoother solution if your condition not just from 0 to little t, but from 0 to the endpoint capital T. And if you compare now this Lagrange data assimilation framework with this more general equation, definitely this Px will be this A1, right? And A0 will be 0. And this little case A0 will be this F. This little case A1 will be this gamma minus gamma, and Y will be U, X will be X. So this Lagrange data assimilation framework perfectly fits into this general equation. So now with this framework, the first thing I want to present is this lambda, Lagrange Euler multi-scale data assimilation method. So the motivation is the following. So what we say, if we have more available Lagrange tracers, it's always useful because it will provide us more observational information, right? So theoretically. However, we also need to worry about our computational cost because if we have a lot of these tracers, then the system of data assimilation can become much bigger. And computationally, we may suffer from some problems. Another issue is that if these tracers, they are not interacting with each other, that's fine. But in many practical applications, the trajectories of Lagrange tracers may also be affected by the additional external forcing sources. So for example, if we consider sea ice flows, different sea ice, they can hit each other. And this is called collision. And the collision is really difficult to model, and it happens within a very short time window. So how to model it is still a big challenge. And that will definitely affect the scale of data assimilation if your forecast model has a lot of model error. So that's why we try to think about if we can, build this Lagrange-Euler data assimilation framework. So of course, the idea of using this mixed Euler and Lagrange measurements in data assimilation has been applied in many practical problems, and these are some very nice papers you can look at. But I want to highlight the difference here. So the difference is that now we only assume the direct available observations contains only Lagrange trajectories. And all these Euler observations in the lambda framework are induced from these Lagrange trajectories. And our goal is to build a multi-scale modeling and a data assimilation framework. So let me tell you something about more details. So look at this figure, panel A here. We have many of these Lagrange trajectories, right? So as I said, if we want to do a direct Lagrange data assimilation, either the system can be a really high-dimensional problem, or they may suffer from collisions if you consider sea ice. But what if we try to build a mesh weight of this system? So let's say we have this pretty coarse mesh weight. And if we can compute some statistics of the Lagrange trajectories within each weight, then these statistics will just be a representation of some quantities within each weight. They will not move, right, because we have fixed this weight. Then we will have a chance to change this problem from the Lagrange observations to the Euler observations. And Euler observations means we always observe the statistics within each of these fixed boxes or fixed cells. So the Lagrange trajectory will change, so the statistics will also change, but their location will be fixed. So that's the underlying idea. So something I think as very, very simple as you can see the number of the trajectories or the number of tracers within each weight cell. That can be one simple statistics. Of course, dynamically, a better way is to use some momentum, which I'll show in next page. So if we can get the statistics on these coarse weights, then we can easily apply Euler data assimilation. And particularly, if we care only about the large scale features of the ocean or of the flow, then this can provide us a very cheap method to get solutions. And the reason we call that multi-scale is in some situations, we also want to get the refined details within each box. Then different from this coarse mesh grid, we use Euler observations. Within each box, we can use Lagrange trajectories. And the nice thing is, for different boxes, we can run Lagrange data assimilation in a parallel way. And then this can significantly reduce the computational cost when we use this parallel computing. So I slightly changed the model here. So for the particle model, we have dx over dt equals v times plus the noise. And note that this v is not the velocity of the ocean, but this is the v of the velocity of the tracers. So we assume the tracer and the ocean, they have some slight lag because the tracer will suffer from the drag force from the ocean. So that's why the velocity, the time evolution of the velocity of the tracer will equal to this drag coefficient times the ocean velocity minus the flow velocity. And we will also have some models about the flow. You can use OU processor to describe that. But still, this will belong to the previous framework. So the next thing is how to develop equations to describe these Euler quantities. So the idea is to use this so-called Boltzmann equation, and that's a method which was originally proposed in the statistical physics, especially for thermodynamical systems. So basically, it tells you if we have the number of tracers goes to infinity, then we can write down the statistics of these tracers. So the details are not important, but with that Boltzmann equations, we can derive, for example, the number of density at each grid cell, we can also derive the momentum equation at each cell. So the momentum can be computed by looking at the momentum of each tracer. Because we can observe the locations of a tracer, we can easily compute the velocity by using the numerical derivative. It will introduce some error, but because we are doing an average within each box cell, then we will have a great chance many of these errors can be cancelled out from the central limit theorem. So then this kind of equation can be used as the observational equation because it describes the momentum of the tracers, but on the right-hand side, it is a coupling between the ocean velocity and the flow velocity and the tracer velocity. And we'll have an equation for the ocean. So this will be the nonlinear equation for the observation, and we'll have the linear equation for the flow field. I only show the momentum equation, but you can easily go from the Boltzmann equation to derive angular momentum or other equations depending on the applications. And interestingly, if you write things in this form, and this still belongs to that conditional Gaussian framework. So again, you can use analytical formula to solve the equation instead of using ensemble methods. So I will show two quick numerical results. So the true flow field here is an incompressible flow, and it contains 80 spectral modes. In total, we have like 2,000 particles. And here we consider the collisions between particles just to mimic the CS case. We randomly choose 40 of these particles to do Lagrangian data assimilation. And you will see like these two different results in panel A, B, and C, D. So both of them are Lagrangian data assimilation results. So the difference is in panel A and B, when we run the forecast, we simply ignore the contact force from a collision. And this will for sure introduce a lot of error, right? But the thing is, first, we don't know how to model the contact force accurately in practice. And the second, we only choose a subset of the tracers. So it's really, if we cannot observe the other tracers, if we don't use them, then it's really hard to compute the contact force, even if we know the contact law. So then you can see the blue curve is truth. The red one is from our data assimilation. And there are a lot of errors here because we ignore the contact force. So in practice, people always say, okay, there will be this model error, but we can always try to do some noise or covariance inflation trick to mitigate some of the model errors. So that's why, we slightly change our equation of the velocity for the tracers by adding this noise. And we hope this noise can effectively represent the statistics of the collisions. And indeed, you can see this will help to some extent, right? The solution will definitely be more accurate than this one. But still, if we look at the pattern correlation with different noise inflation coefficient, this red curve, you see the pattern correlation about maybe 0.65. So it's better than this one, definitely, but it's still not very great. So now, since we realize there are a lot of these collisions, so we try to use this Euler data assimilation. And the motivation is that, when we compute the average within each grid cell, then these complicated collisions may just cancel each other. They are kind of noise, right? Then you can see our results can become much better compared with the previous two. And actually, the pattern correlation here is about maybe 0.85 or maybe even 0.9 on average. And the truth and the recovered flow field, they are pretty consistent with each other. And the second example is about this multi-scale data assimilation. So we consider more modes, and we have 3,000 non-interacting particle flow field. And here we can say non-interacting flow field, non-interacting particles, because we want to look at the multi-scale features. So for the larger scale features, we use Euler data assimilation, and for the small scale features, we use Lagrange data assimilation. And the true flow field is here. You can indeed see the multi-scale features because we assign the same energy to all these modes. So it's not like the energy will decay from large to small scales, but the small scale modes will be very energetic. And we try to do so because we want to mimic the actual nature phenomena with these chaotic features. And And you can see here, this 1 minus 1 mode is from the Euler data assimilation. The truth and the posterior mean is pretty consistent. And for the small scale mode, we use Lagrange data assimilation. And note that here, there will be like, I don't know, 500 modes maybe. So within each box, we only have maybe 7, 8 particles. So it's not a great number, but still, you can still get pretty accurate results for the small scale. So here we compute the scale score of the average behavior of the large modes and the small modes. And you can also only focus on the red curve, which is pattern correlation. You can see it's pretty good. And we also check what if we just ignore the small scale modes. Then if you only want to use Euler data assimilation to recover larger scale modes, then compare with the entire field. Actually, the accuracy is not that great. But once you do this multi-scale data assimilation, you can have a significant gain for the overall result. And this is truth. This is a larger scale result. They are not similar, but you can capture some larger scale behavior. And these are the small scale results. This is the total flow field. And the total flow field recovered is pretty similar to the truth. So in my next 25 minutes, I will try to discuss UQ questions related to this Lagrange data assimilation. So the first question I want to ask is, let's say we don't consider collision, but we have maybe different numbers of Lagrange traces. And want to ask ourselves, what will be the data assimilation scale, or what will be the information gain as a function of number of the traces in this Lagrange data assimilation, right? So intuitively, without collision, if we have more and more traces, we should have better and better results. But we want to quantitatively assess how is the improvement in this setup. So again, we consider incompressible flow, and this is our framework. So basically, we want to compare these two things. The first thing is our prior distribution, which is a distribution based only on our model. That is, we don't use any Lagrange trajectories as our observations. We just run our model forward for a long time. We get an equilibrium distribution. That's all what we know if we have no observation. And the second thing is we have this posterior distribution, which is a conditional distribution of our model state given the observations. And this one, it will incorporate the observational information. And if we can quantify the difference between these two distributions, then definitely the additional information or the additional gain will come from these observations. And we'll play with number of observations to see how this information gain will increase. So before that, we can actually do some additional work. So we can show that if the flow field is incompressible, then the distribution of the traces in this 2 pi square domain will satisfy this uniform distribution. And the reason is very simple. If your flow has no bias towards convergence, divergence, then your tracer should be located everywhere with the same probability. We can also show that if we have infinitely many number of traces, then if we have no model error, then eventually the posterior mean, which is this one, will converge to the truth. So that's a good validation test, saying that without model error, if we have infinite number of traces, we will perfectly recover the flow field. It is consistent with our intuition. But now we want to really quantify the difference between the posterior distribution and the prior distribution. So it's a comparison between two distributions, so we cannot naively just take the difference between the two distributions, right? We have to think about a better way to quantify the difference. So the idea here is want to directly compute the difference between two distributions, and we use an information criteria which is called relative entropy. So this relative entropy is an unbiased measurement to quantify the lack of information in one distribution compared with the other. And it is represented by this formula. You have a posterior times your log posterior over prior, then you take the integration. Because now we have this perfect model setup, and our prior and posterior are both Gaussian. Prior is Gaussian because it satisfies this OU process. posterior is Gaussian because it's conditional Gaussian given the trajectory. So if both of them are Gaussian, then we can actually avoid using this high-dimensional integration, but instead we write down this relative entropy into this analytical formula, and it contains two parts. So the first part basically checks the difference in the mean, in the prime mean and the posterior mean. So we try to add an inverse of the covariance to cancel the unit of this variable, because variance has a square of the unit of the variable, but mean has the first pole. But you have this mean appears twice here. And dispersion basically checks the additional information in the covariance, meaning that if your covariance it shrinks a lot, then they should become much more significant. And K is the dimension of your system. So basically, we use this analytical formula to separate the contribution from the mean and from the covariance, roughly speaking. We can show this in a rigorous way. When this number of traces goes to infinity, then we can show that the signal part will converge to a constant. And this constant is you replace the posterior mean by the truth, and everything else is the same. And this is, of course, consistent with this conclusion, right? If L goes to infinity, then the posterior mean will converge to the truth. So now here, when L goes to infinity, you simply replace the posterior mean by the truth. So roughly speaking, this is valid. And it tells you, if you have more and more traces, you will get better and better estimation of your posterior mean, and it will eventually converge to this constant. So this constant may not become zero because the truth is just one realization from your equilibrium. Equilibrium is, it's an equilibrium, model equilibrium, but truth will have some variability there. But it tells you will have a good convergence. But the interesting thing is about this dispersion. You may expect, if you have more and more traces, I can also reduce my covariance. That's true, but the thing is, the dispersion part, it will never converge. But instead, you always have some gain. So the dispersion will be proportional to the log of this L. L is the number of traces. So that means if you put more and more traces, you'll always have some gain. But the thing is, this gain can become slower and slower. Just like this figure, which is a comparison between theoretical and numerical result. So it's an uncertainty reduction in the dispersion part, basically this equation. So if you have a small number of the traces, if you have 1, then increase that to 10, you'll get a huge gain, right? Your covariance will shrink a lot. But once you have more and more traces, this increment becomes slower and slower. That means your covariance will shrink slower and slower, which makes sense, right? You cannot have the same rate. You cannot make the covariance be negative. But it tells you like two types of information. One is you can always get information gain. The second thing is you will have this practical information barrier. Like if I tell you, I will give you 100 traces. So if you have no tracer, you increase that to 100, you gain a lot. But if you want to gain a similar amount of information from 100 to whatever, then you need many more number of traces to reduce the same amount of information. So in practice, we do not have infinitely many number of traces. So we need to stop at a certain point. So that tells you, after a certain point, if you add more, then you will just get marginal increment, and maybe you shouldn't do that. And this final result just a validation of the signal part. So it's a truth. This is a result with 2 tracers. If you increase to 10, you can see you're almost be the same as truth. Then you increase to 50, you don't see a lot of improvement here, right? Again, this tells you maybe in this case, 10 is good enough. The other 40 will give you a little bit gain at most. So maybe the last topic I will focus here will be this eddy identification. So again, this will be something ocean scientists care a lot about because these ocean eddies are dynamical rotating structures in the ocean. And these mesoscale eddies are something they care particularly about, and they are the major drivers of the transport of this momentum, heat, and mass, and a lot of this biochemical and biomass transport and production in ocean. And ocean eddies is something related to climate change, especially the ocean eddies in the Arctic area. People try to understand how climate change affects Arctic and the global climate system. So there are a lot of different criteria to validate these ocean eddies or to identify ocean eddies. And some are based on the Euler criteria, some are based on the Lagrange criteria. So the focus here not to compare these criteria, but instead, I will only focus on this so-called Kubowice parameter, which is one of those widely used criteria. It's a very simple criteria, it's the most widely used criteria, and it's very easy to compute. So I will use this criteria for the eddy identification study here, but my focus is on the uncertainty when our estimation not accurate. So this OW parameter is based on a very simple combination of three different terms: the normal strain, the shear strain, and the relative vorticity. And when this we call it OW parameter is negative, then that means the relative vorticity means you have this rotation. So it will be larger than the strain component. Then this basically means you will have an eddy. And it is an Euler quantity based on a snapshot. You can easily build other Lagrange type of the quantities if you want. So why we want to think about uncertainty? Because significant uncertainties may appear in the state estimation. For example, in the Arctic region, we can not directly observe the ocean, but we can only observe the sea ice flows. And we want to use Lagrange data assimilation to recover the ocean from the sea ice flows. And from this recovery, we know we'll have some posterior uncertainty, and that can be large in some areas. And we want to look at how that uncertainty will affect eddy identification scale. So in the past, many of these identification studies, they were done based on the mean estimates of the flow field. But if we know the uncertainty is large, then the mean basically will tell you nothing. And such mean estimation can lead to very large bias because of the ignorance of the uncertainty. So nowadays, there are many very nice reanalysis data sets which contain ensemble members. And these ensemble members can be effective ways to represent the uncertainties. So before I show more comprehensive results, I just want to show some very simple mathematics. Just say if we have a variable that is a random variable, you can always decompose that to its mean and its fluctuation part. And the fluctuation part basically represents uncertainty. So if we use a classical method, we just look at the posterior mean or any mean value, you compute the OW parameter, then this will be very different from computing this OW parameter for each realization and then taking the mean. And the difference is because this is a nonlinear quantity here, right? So you know, with this fluctuation part, you should have some closure terms or the residual terms. So by directly computing the mean, that will not be sufficient. You will have some additional terms that will tell you the uncertainty. So like in this very simple example, this is a true field. This is OW parameter based on the truth. And if you have a large uncertainty, then you average over all the realization, you compute this OW, that will be this result. Basically, you just identify one eddy. If you look at different realizations, then you take the expectation, this will be the result. You will get maybe slightly better results, and you have some improvement. But again, this is not enough. So that means we need to think about this from a probabilistic viewpoint, not just showing the mean, but showing the entire distribution. So then the idea is the following. We can use Lagrange data assimilation to recover the flow field. Then the recovered flow field will have some uncertainty. So we can sample trajectories from the posterior distribution, especially with the previous analytical formula. The sampling can become very efficient. Then for each sample, the trajectory, we can compute the OW parameter. I mean, first we compute the ocean flow field, then we compute the OW parameter. So we have a bunch of these fields, each represent one OW parameter. Then this will give us the distribution of the eddy identification. And this is very different from getting all these flow field, taking the mean, then apply a single OW parameter. And the framework is not limited to OW parameter. It can be used combined with other eddy diagnostic methods, and it can also handle extreme events pretty well. So I show some quick results. We consider a 2-layer QG model as our choice with 128 square resolution, and we consider Arctic region in the marginal ice zone with 32 flows. So this is a typical number according to the observations. So this figure basically is a snapshot of the ocean field and the Arctic sea ice flows. On top of that, you can see they are pretty sparse, but these Arctic sea ice flows can be used as Lagrange traces to recover the ocean. So this figure shows at one single time instant, these are all the identified eddies. These are not traces, these are eddies. So each black dot means there's one eddy here. And this is a method, if we just use a Poisson mean, we ignore all the uncertainties, you can see maybe 50% of the eddies, but the other 50% will just disappear. And this one, it uses all these distributions. So most of these eddies will be assigned a certain percentage. They're not 100%, but it'll tell you there will be a chance there will be an eddy here. And this is a specific case study. So this is one eddy, this is second eddy, this is third eddy. So the third one is very strong. The first one is moderate. The second one is a bit weak. And what we compute here is the lifetime of the eddy. Basically means how long this eddy will last according to this entire period. You will see this red curve, which is the equilibrium distribution without any observation. Just saying we run the model for a long time, we collect all the eddies, then we compute the lifetime, we form this distribution. So it's kind of a prior knowledge. And the black solid line here is the true lifetime of each individual eddy. And the blue one is from the probabilistic eddy identification. It will give us a distribution. And this distribution is definitely very different from the prior. And this dashed line is a value where you only use a mean to estimate the eddy lifetime. So you do a data assimilation, you forget all the uncertainty, you take the Poisson mean, then you compute the OW parameter. So this is always very different from the truth. And in many cases, this distribution can actually cover the truth pretty well. So this is maybe an outlier, but still, it will tell you this will be an outlier. But the main only method will just give you a single value without any uncertain quantification. And it is very far from the truth. So I can briefly mention about the last topic. It's about how to optimally deploy Lagrange traces. And the motivation is that, if you know the true flow field, sure, you can use geometric properties of a flow field. You can say where I should put the traces. But the thing is, you never know the truth. You have to estimate the flow field. Then based on that uncertainties, you try to design strategies. So we developed some optimization criteria, which are based on this information measurement. Again, we try to see if we can get a maximum information gain by adding additional traces compared with the prior distribution. So this can be a very nice optimization cost function. But the thing is, computing this is very expensive, especially each time you have to run data assimilation to compute the posterior. So although mathematically it's nice, practically it's almost impossible to do. And therefore, we propose some approximate cost function using the so-called Lagrange descriptor, but we put some uncertainties here. These are some details, but the final result is that we can save a lot of computational cost if we use this surrogate cost function. And the actual value is not too far from the brute and force experiment. Brute and force is based on like a simple experiment. That's all what we can afford to do the validation. Okay, so summary. So basically, the talk contains two parts. The first part is about the mathematical theorems and schemes of Lagrange data assimilation. So we propose this analytically solvable Lagrange data assimilation with continuous in-time observations. Then we introduce this lambda framework, where the Euler observations were induced from the Lagrange traces. Then we discuss some UQ questions. First is how to rigorously quantify the information gain when the number of traces becomes large. And the second is how this uncertainty can help us better identify the eddies. And the method can also be applied to this optimal design of deploying the traces. So I guess I'll just stop here. And thank you very much for listening to my talk. And I look forward to some feedbacks.
Thank you very much, Nan, for this very interesting talk. Are there any questions? Okay,
Yeah, great. Maybe I can ask a question. Great talk, Nan. Thank you very much again. One question for the on the CI's application, like on the flows, like if you were to use what your development, modeling like the flows as a Lagrangian observation, or at least as a Lagrangian model, does that always make sense, or are you thinking that you could also, model that as a field, in particular once you have a lot of them, but maybe the Lagrangian approach is fine?
Yeah, exactly. I mean, that's a very good point. So actually, it's still debatable in the CIS community. So in the past, people always use this continuous form. They use this Euler framework to describe CIs. But nowadays, because of this climate change, in the we call that marginal ice zone, the density or the concentration of the CIs becomes much lower. And that made us to think about maybe we can use Lagrange ways to describe these CIs. But if the concentration is high or the density is high, definitely the Euler method will be much better, because the collision will basically kill all the skill of Lagrange decomposition. So I guess in practice, it should be a combination of these two different methods, depending on the properties of the problem.
Got it. See, so thank you very much.
Yeah, thank you.
Ryan, go ahead.
Sure. Okay, very nice talk, Nan.
Thank you.
Really nice. So I have a question about maybe somewhere around slide 10 or so. I mean, maybe I didn't quite understand. It's so basically, if I understand correctly, you're actually developing these more efficient models. They're stochastic in nature, to be able to.
Yeah.
I'm sorry.
It's here, right? It's page 9.
I believe so. Yeah. Right. Right. And I'm just wondering, I mean, so my understanding is that you're developing them and then you're calibrating the statistics so that they match as close as possible the data, which is a very good idea. And I'm just wondering whether you can do the other way, if you can just take the very, what I'm getting at. So if you just take the full order models and then do something like a very reduced order model and then add some statistics, would that also be something to consider?
Exactly. That's, I mean, actually, the point is exactly as you said. So I didn't say too much here. But the thing is, one big advantage of doing this method, not just to save the computation cost in calculating these nonlinear terms by using noise. But another thing is, when you solve a PDE, you have to make sure you have fine enough resolutions when you do spectrum method, right? Because these different modes are coupled. Even if the small scale mode, they don't matter, you have to include them. Otherwise, the solution can be unstable. But now everything becomes decoupled. You can just run a small set of the modes. You don't need to run 128 square. You may just need to run like 16 square. So that will be a very important way by combining with the reduced order models in this forecast.
Okay. Thank you.
Thanks for asking this.
Any other questions? Yes, Pierre?
Yeah, if I may ask, I have another one here. So here, you may have answered this, and it may be a stupid question, and I apologize for that.
No,
but
definitely not.
So if I look at the posterior distribution of either of you, in the forecast in this model, and if so, I view K at. So if UK at the T0 is Gaussian,
Mhm.
then, you know, assume if the noise is Gaussian, like the UKT hat will remain Gaussian, right? Since it's
Yes.
linear.
Yes.
And then even though, you know, the like observation process, right, may, I mean, again, it depends on the properties, may not remain Gaussian. Where I'm going is that if you go back to the flow field, right, so the U, which is a sum of the UKs hat, when if the UKT hat at T0 are Gaussian, are the UKXT always Gaussian?
For this one,
That's
yes. For this one, yes. So if we start from a Gaussian, then it will always be Gaussian if the dynamic satisfies this linear Gaussian process. So
got it. Regardless of what the observations are, right? So
right. I
is
mean,
that correct?
so
Or the observations need to be Gaussian as well?
so flow field, because it's like one-way coupling here, right? So the flow field will not be affected by observations. The distribution of traces are definitely not Gaussian. It can be uniform distribution, but it's a distribution of tracer. So the distribution of this U is always Gaussian if you start from a Gaussian initial condition. And the observations will not affect the flow field. It will contain some information because it's driven by the velocity field. And it will be important when we do data assimilation. But just if you think about the truth of the velocity field, it will be Gaussian because it can be completely determined by this single equation here.
Got
Yeah.
it. Okay. Thank you.
Of course, I mean, we use this approximation, and you know, in some situations, the true flow field may not be Gaussian. So that's another source of the model around uncertainty. And there are other ways to handle that issue, but for simplicity, I didn't discuss too much here. I just assume the simplest possible setup.
Yeah, correct. Yeah, I was just wondering. Yeah, got it. Yeah, for with assumptions, what can you say? Yeah. Okay.
Right. Yeah. Thank you for asking this.
Other questions? I have one. If nobody. So I don't know if it makes sense, but so you in your approach, you're using data from the tracers, right?
Yes.
Would it make sense to include other data, like, I don't know, if like surface elevation or something else?
Right. Yeah, definitely. So I think there's a very important question. Actually, I think Pierre did that maybe. So you try to combine different sources of observation. Some are Euler, some are Lagrange. And I think Pierre did some Bayesian framework to decide which or how to combine them together. And in practice, you have all these different sources. You have different observation noise, and many of these data are sparse. So some optimal design will definitely be something very important. And we try to do something, you know, to optimally determine where this Lagrange tracer should be. But you are definitely right. If we have other Euler type of observations, and they should also be incorporated, but we need to think how to do that in an optimal way, depending on what kind of quantities you want to recover. You know, then case by case, you can design some strategies.
Awesome. Thank you.
Yeah, thanks.
Any other questions? Okay, well, Ryan is saying great talk, Nan, and he's calling this very interesting seminar. So thank you, Ryan.
Yeah, thank you. Yes, I want to thank everyone for attending this seminar. Thank you.
All right, well, stay tuned for the next community meeting.
Correct. Yeah, thank you very much. Thanks a lot, everybody, and have a good end of the week. And thank you again, Nan.
Thank you.